also try to provide at least an excerpt of this book. I'm not, of course, allowed to give you the book online, but the editor allows me to give you one chapter, for example, so I'll try to provide it, where the technical derivations are made, and you will find more details in this reference. As you will see, there will be quite an overlap with the lectures of Jérôme, and it's the hope that by having two lights thrown on the same object from two different directions, it will help for the understanding. So don't hesitate to ask questions, don't hesitate to interrupt. I have a natural tendency, maybe I should take the mic. Yeah, it's not a problem. I think it's not so much for the voice, but for the recording, if you want to record something. It's on. Okay, now I have to find the right topology for this thing, which is always difficult. Okay, so is it working, and is it not blasting the drums of the people who are... No, okay. So I was going to say, if you don't interrupt me, I have a very simple natural tendency. I accelerate. Further. Here it is. Okay, perfect. So do interrupt. Otherwise, it will go faster and faster. I have a last question. How many of you heard or have worked or at least vaguely know the concept of Fermi liquids? That's much less. So, okay. So before we start the course per se, let me give you a crash course on Fermi liquids, because I know that you're principally interested in low-dimensional systems, but I think if you want to have an idea of what we're going to discuss, it's still good to have maybe a little reference of what exists in other dimensions. And I want also to tell you why we are interested in one-dimensional systems, why we are doing this. So let me do with the slides, because this is not the main focus. There will be no technicalities in this part. And again, I won't go in details concerning the calculations or whatever, but you can find much more details in these three set of lectures. This is a master course on many-body physics, so this is a very simple set of lecture. And these are two more advanced courses that were given in the Les Houches school, where you can find more details. So let me backtrack a little bit and tell you about materials. After all, humanity wants to master materials. You know that all ages of humanity have been called after a single material. You get the Copper Age or the Bronze Age or whatever, so it's really something important. And unfortunately, the only thing we understand really, and I'm sure you all suffered during your courses with that, are free particles. We understand free electrons. The little problem is that if you take any realistic material, you can take aluminum, the simplest, best conductor, the most stupid material you can think of, the interaction, the order of magnitude of the interaction energy in a material is of the same order than the kinetic energy of the particle. So the kinetic energy of particle in a material is of the order of 1 electron volt. This is the Fermi energy. And if you put numbers on Coulomb interaction in a material, you find, again, 1 electron volt or 10,000 kelvins. And so technically, one should throw away everything you learned in textbooks or in courses on solid-state physics, because there shouldn't be a single material which should be described by free electrons, by free particles. And the reason why we can still use this for properties of realistic systems has been provided to us by Landau here. And the essence of Landau's theory is that there are excitations, which are called Landau quasi-particles, so I also use quasi, which look like electrons in a way because they are quantum numbers. The quantum numbers for the excitation are the one of an electron, but they are rather complicated objects. They are electrons dressed by density fluctuations of the other electrons. So this is like an atom dressed by electromagnetic radiation, so by many photons. You have one particle which interacts strongly with the others, but at the end it gives an entity which behaves roughly like a free particles. And this is incredibly successful. Okay, there is a price to pay. You need, of course, to change some physical parameters, like the mass of these objects. And with that, you can forget about interaction in many materials, and therefore we have the possibility to use what we learned from free particles. So for example, for free fermions, we know that the momentum occupation is a step function which has a sharp discontinuity at kf, or in energy at the Fermi energy. These are fermions, of course. So if I have interactions, you could imagine this is rounded, but no, what Landau determined is that there is still a jump of the momentum distribution of particle at the energy EF. Of course, the jump is reduced a little bit by the interaction. So this is what people call the quasi-particle weight. So not the whole electron is in quasi-particle state. In the same way, if you look at the probability to measure an excitation, a single particle excitation with momentum k and frequency omega, then for free particle, of course, it's a delta function. You only find the excitation if the frequency matches the energy of the particle. With interaction, it's not a delta function, it's a potato, or also called a Lorentzian, which gets thinner and thinner as you get closer to the zero of energy, which is the Fermi energy. So very close to the Fermi energy, you can view this excitation as nearly free excitation with a lifetime. So just to give you this, of course, you can measure this, for example, this probability of having a single particle excitation with frequency omega and momentum k. You can measure this with a technique known as photoemission, where you throw photons at the material and this extract one electron. And if you use this technique, just to show you a little bit the thing that you get measurements. These are measurements that were done on a stupid niobium. This is done as a function of the energy, and you see that this is the momentum distribution, so or the energy distribution, if you want. So you see that you get something which is rounded, but you see that the rounding is totally controlled by the temperature. So this is perfectly consistent with the picture, with the picture that I showed here. Where you should have a discontinuity at zero temperature, just like for free particles. Okay. I don't want to go too much in the details. You can show this theory perturbatively in the strength of the interaction, but the point is that it's much more general. It works even in the interaction is not small. Here I show you some numbers for various elements. So for example, just to give you an idea of the importance of the effect, one can look at the change of the mass of the quasi-particle compared to the mass of a free particle. For niobium, it's a factor of 2. You see, it's not small. It's not 1.00001. It's 2, which means a straightforward perturbation theory tells you that the perturbation in interaction is as strong as the kinetic energy. But you have materials which are called heavy fermions, which are horrible materials with uranium, cerium, and blah, 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 for which the renormalization of the mass can be 100 up to 1,000. So this is really telling you that this is robust and very efficient, way beyond perturbation theory. Now, this has drastic consequences. For example, the fact that you can use free theory tells you that, of course, for fermions, you know what is a metal, what is an insulator, what is a semiconductor. So you can invent the transistor. If you think about it, I don't know how many of you are familiar with the theory of superconductivity. You probably all had a course on theory of superconductivity. And I don't know who gave you this course, but they cheated. They told you that you take free electrons, and then you had the tiny, weeny, very small attraction due to the phonons. And nobody complained that you throw away the huge, big Coulomb repulsion between these electrons, which would normally wash out completely the tiny attraction between the particles. So you have an attraction which is of the order of 100K, and you throw away a repulsion which is 10,000K. This is crazy. Of course, the person who gave the course didn't cheat, because what are the free electrons are not free electrons, they are the lambda quasi-particles. And the lambda quasi-particles are sensitive to the small attraction. So if you have Landau Fermi liquid theory, you can invent superconductivity, and just for fun, here are the Nobel Prizes. And closer to us, there is an effect which is called giant magnetoresistance, which tells you that the resistance of some materials can be extremely dependent on the magnetic field you apply on it, which was the Nobel Prize of Fert and Grunberg in 2007. So I choose this example just to show you that Landau Fermi liquid theory was the root of not only fantastic discovery in fundamental science, but if you think about it, transistor completely changed our lives. I can do what I'm doing and being recorded thanks to the invention of the transistor. Superconductivity is used in labs, in hospitals, to produce the magnets which are used for MRI. So it's also, hopefully not too often in your lives, but it's there. And giant magnetoresistance was used to change all the industry of magnetic recording. So for a while, all hard drives in computers and iPods and whatever other mobile device were using detection of information that was based on giant magnetoresistance. So in a way, you can say that the 20th century was the century of Landau Fermi liquid theory. Now we've changed century, and now we need to find new materials. And new materials means we want to have materials that can harvest heat and produce electricity, or can produce light from electricity, or can produce electricity from light. If you think about it, the CCD camera in your, all your phones are exactly this. They produce electricity out of lights. So you want materials like this. And for this, we need to make work together the spin degrees of freedom, the charge degrees of freedom, the orbital degrees of freedom. And it's very difficult to imagine one can do this without understanding the interaction. So the problem that has been swept under the rug for, let's say, 60 years, thanks to Landau, which is what happens when you have 10 to the 23 particles in interaction, now we have to solve it. Of course, you won't write 10 to the 23 equations, that's a little bit too much. And because of the fermionic nature of the problem, even if you go to a computer which is able to do 10 to the 15 operations per second, you're dead. Because there are effects which are called sign problems and so on, which cause numerical instabilities with fermions, which make this problem incredibly hard to simulate. So essentially, we are faced with a very strong problem. We need to understand it. And this is what is known generally as quantum many-body. And of course, as I said, it's a beautiful theoretical problem, which is the only aspect that I will be interested in these lectures. But it's also a problem which has drastic consequence, drastic practical consequence. Okay. Now, in addition to this, people have realized that they must look in less and less dimensions. Why? A, because typically size of device is decreasing. If you look at the integration of transistor in any circuit, you will find that it's completely exploding and reaching sizes which are now very comparable. This is already old, this is 10 years old essentially, reaching sizes which are now comparable with atomic sizes. So at some point you cannot go down in size below 1 atom. So, but it means that already the time to look at materials where you say I have 1 cubic centimeter of material and that's what I want to know is past. What you want to know are objects of essentially either 0 dimension or 1 dimension, or films, 2 dimensions, and so on and so forth. So there is a pressure to look at lower and lower dimensions. That's a practical pressure. Now, there is also a fundamental pressure, which is that a lot of interesting physics happens at the edge of materials. And I think that one of the first person to have understood this is Bert Alprin. For example, if you look at materials which are 2D semiconductors under a magnetic field in which you have the fractional quantum Hall effect, what you realize is that the Landau levels, which are in the material, just go up at the edge, so the only part which is conducting, the bulk is insulator, but the edge of the material is conductor. And this is something which now has become, I would say, run-of-the-mill in the sense that there are other materials, I'm sure you have heard about topological insulators and so on, in which the bulk is essentially boring, but the surface of the material, in that particular case, the surface is a one-dimensional object, because the material is 2D, the surface is 1D, is interesting. So we have also a new class of problems that occur and which are essentially prompted by looking at the edge of materials. There are, of course, many other experimental motivations that we will discuss. So I will focus on one dimension. Of course, 2D is beautiful, 3D is beautiful, but I will focus on one dimension. I could give you this reason, which is due to Freeman-Dyson in 1967, which says essentially that the reason to look at one dimension is that it's fun and that it will refresh the imagination of a theorist better than a dose of LSD. So I prefer strongly working on one-dimensional problems. I think it was a sign of the time, that 67. Anyway, that's a good advice from Freeman-Dyson, work in one dimension. I just more seriously want to motivate it by two things. I told you about Landau Fermi liquid. Essentially, the fact that even very strongly interacting particles behave as individual particles. In this room, you have an infinite repulsion among each other. You cannot be two of you at the same place at the same time. Nevertheless, you can essentially behave as free particles because you can avoid each other. If you are in one dimension, and I'm sure we will discover this when we'll queue for the lunch in a moment, you cannot behave as an individual, because if you are in a line and you have interactions with a person or objects which is before or after you, if this object moves, then it pushes this one, which pushes this one, which pushes this one. So all motion has to become collective. So that's one dimension is completely different from 2 or 3 or 4 in the sense that it's very difficult to get individual motion. And as we will see, any small interaction will destroy completely individual excitations, will destroy individual particle and transform everything into collective motion. The second motivation, that's another example that you can experience. The second motivation is that on the theoretical level, we are used to certain tools, and one of the most useful tools that we use is usually mean field theory. We say, oh, if we have a certain phase, like superconductivity, we just, let's say, assume that there is a mean of the other parameters. So here, for example, would be the wave function. And if I have a superfluid, I would say the phase of the wave function is fixed. And then I would say there are small fluctuations around this average. In one dimension, as we will see, because of quantum fluctuations, and of course thermal fluctuations, but even at t equals 0 quantum fluctuation, it's very difficult to order. There are theorems which tells you that you cannot break a continuous symmetry, which means that all this mean field stuff essentially goes directly to the garbage can. So we need to find other theoretical tools, we need to find other ways to attack the problem, and fortunately there are other ways, but it also makes the problem quite interesting. So to summarize, 1D physics is very different from the higher dimensional physics, and in addition, as we will see during the course, there are actually many experimental examples. Because this is not obvious, it sounds like a theory game, but both in condensed matter or more recently in cold atomic systems, there are really an explosion of one-dimensional systems. I would like to destroy 3 urban legends on 1D, and that's why I'm telling them to you now, but we'll come to that. The first urban legend in 1D is that 1D is a toy model to understand higher dimensional systems. You usually hear people say, oh, I cannot solve the problem in 3D, so I try to solve it in 1D. Yes, it's simpler sometimes it's more complicated, but very often it's very different. So it's not, you do not solve 1D problems because you just want to understand 2D or 3D physics. They have their own life, their own characteristics, and that's important to keep in mind. The second urban legend is that 1D does not exist in nature. It's just some theoretical dream. That's completely wrong, and we'll see many, many experimental examples. And from that point of view, cold atoms really helped putting 1D really on firm basis, but not only. In condensed matter, there are many, many examples. And finally, the worst urban legend of all, which is very pernicious because indeed a lot is understood in 1D. But if you have a field in which everything is understood, the natural reaction is to say, well, let's do something else. And what I would like to convince you, and of course not in this lecture, I will start with things we understand, but I would like to keep the fifth lecture to show you that there are many open problems which are incredibly hard and which need, of course, talent, imagination to solve them. So the world of 1D is not at all closed. There are a lot of things to understand there, and we need to get rid of these three urban legends. Okay. In addition, as I said, there is a drastic evolution of the 1D world. There are a lot of new methods which have appeared on Bethe-Ansatz, numerical methods that I will briefly mention, but I'm sure Frank Verstraete already talked to it last time. New systems, new experimental system called atom magnetic insulators, and finally a lot of new questions, of course, in particular effect of spin-orbit coupling out of equilibrium and so on and so forth. So it's really a fantastic world. If I can tell a little particular anecdote, when I wrote my book on one-dimensional system, it was out in 2004, and I thought it would be stable for a long time. And 10 years after, I won't say the book is obsolete, I hope not, but there is literally 200 pages that must be added to this book, which is sort of half of the size of the book, because of the new material that occurred in the 10 years that were in the interval. So this is really something very exciting to see a field which has evolved that way. Finally, we are entering 1D, so I will stop the slides. Yes, we are not in Kansas anymore, definitely. We are living the comfortable world of higher dimension. I just would like to tell you a little bit on the philosophy on how to treat 1D problems before we go on the actual calculations, because it's something which I would say is interesting from, I wouldn't dare to say a philosophical point of view, but from an historical point of view. You can start treating 1D problems like you would any problem by standard many-body theory. And this is something that indeed started the field with Tomonaga, Luttinger, Gorkov, Dialoginski, Larkin. These people took Feynman diagrams, perturbative expansion and interaction, and they started to do extremely powerful calculations. I highly recommend a paper by Larkin and Dialoginski where they resum exactly the series of diagram coming from a perturbation expansion in the interaction. You have to be a very high-powered theorist to really do that. So credit should be given to these people, but that's not really the right way to do it. Then, when this system, I told you, you have to throw away the mean field approximation and so on, but fortunately, there is exact solutions, which goes by the name of Bethe-Ansatz, and let me show you, of course, Hans Bethe, but also Elliott-Lieb, whom you heard the name, Lieb-Lininger, probably already, who were extremely powerful people in this game. In particular, many firsts were obtained by Elliott-Lieb in the understanding of the physics. This is an exact solution. It has two drawbacks, and there I'm sure Fabian will kill me for saying this, but very often the only thing you can say about a model which is exactly solvable is that it is exactly solvable. But you don't know the solution. Then you work very hard, and you can work the solution for a finite number of particles. Then you work even harder, and you work the thermodynamic solution. Then you work even harder, and this takes 50 years, and you can compute the correlation functions. So this is a very, very powerful, but very difficult method, and it has the drawback to be restricted to special models. Then there are field theories, and you already heard a little bit about them, and in particular one method which is known as bosonization, conformal field theory, which was pioneered by various people, but my three main zero are Alan Luther, the late Vic Emery, and of course Duncan Haldane, who didn't get the Nobel Prize for this, but could easily have gotten it for the work he did in one dimension. And finally, you get very recently numerical methods, density matrix renormalization group, Monte Carlo, and so on. Here are the pictures of Steve White and Uli Scholvak, who did substantial contributions. Well, Steve White did the seminal contribution of inventing the DMRG, and bringing also these methods to time dependence finite temperature. So you could say this is the same in every dimension. You always get sometimes exact solution, very rare in more than one dimension, but certainly you always get field theory description and numerics. The difference in 1D, and that's what I wanted to show you with this slide, is that we managed to make these three methods work together. Because if you think about it, numerics is efficient at short distance, short time. If you try to go to large distance, large time, it's a disaster. You don't get the power to do this. Field theory is efficient at low energy, long time, large distance, but extremely inefficient at short distance, short time. And I would say exact solution is, of course, efficient everywhere, but as I mentioned, very difficult to compute correlation functions and also restricted to special model. So if you can make these three methods work together, you can really get the best of both worlds, or the three worlds if you prefer, and get very complete description of many problems. Of course, not all problems, but many problems. And I think that's one thing, that's a take-home message, that I think one of the biggest cause of progress in 1D, independently of the individual progress that were made in each one of these fields, is that at some point we got a way to really manage to make these three methods work together, in great part thanks to Duncan Haldane. And having done this, we can really make a quantitative description of many problems. Okay, so that's so much for the introduction, because I thought it was useful not only to tell you about 1D, but to tell you why we could be interested in 1D. And now we will really start the calculation itself. So, okay. So again, I give you the tentative plans of the lecture, as you will find on the description. I just reshuffled a zest of things. So today we will try to do the basic notion of a 1D system. Then we'll move to more complex things probably tomorrow. And then I would say I've put this, but it's really depending on you. So if you feel I'm saying things you know very well, don't hesitate to tell me. If you feel that I'm going too fast, don't hesitate to slow me down. It's not a marathon. I don't need to cover all this. I've not signed a contract saying I have to cover all this. So we'll do what we do. And we have 5 lectures. So just give the pace, or if there is a pet subject that you would like to hear about, don't hesitate to let me know. I will tell you if I can do it or not do it. So it's really your course, so don't hesitate to interrupt. Okay, so let's start, and let's say we start with the basic notions. So can you see? Perfect. Basic notions of 1D systems. Okay, let's see if I can do it cleanly rather than draw a bad... Okay, so the first chapter, in a way, is very simple, and I'm sure you're already... But what is a 1D system? It's a relatively trivial thing, but before we try to solve, I need to ask you, so what is a 1D system? Because we live in the 3D world. Okay, I'm not talking about string theorists who live in the imaginary axis, but we live in the 3D world. So how can I get a 1D system? How does it work? So let's try something simple. Let's imagine I have particles which are confined in a box in 2 directions, or let's say in 3 directions. So I have here a length L, and let's say I have here a length that I would call little l. For simplicity, I will not consider the 3rd direction, but that's just... So you know, of course, if I have 3 particles, that I have k, and let me put periodic boundary conditions. It doesn't really matter. I can put finite box conditions, if you prefer. It doesn't really change. Well, let's take even finite box condition. Then you know that k, so k, let's call this x. Let's call this z. So kx will be pi over little l times an integer, px, and kz will be pi over big L times an integer, pz. Okay, so energy, or whatever, is simply given by, and I will do h bar equal 1 as usual, kx squared plus kz squared over 2m. And normally, if you live in a normal world, all dimensions are about the same, so everything is fine. But now let's assume that L is large and little l is small. And of course, you could shout small or large compared to what, but we'll come to that. Now, it means that, in a way, if L is very large, I can consider kz practically as a continuous variable. Okay? On the contrary, if L is small, I have to worry about the quantization condition. So what I will draw is essentially energy in a different way. I will draw it uniquely as a function of kz, but for the various quantum number corresponding to px. So I have a first case, which is px equal 1, in which case I start with an energy which is whatever, 1 over 2m pi over little l square, and then I get the parabola that corresponds to essentially the continuous variation coming from kz. Now, if I go to px equal 2, I have an energy which is, of course, the same thing, 1 over 2m, but this time 2 pi over little l square, and then I get again a parabola, and so on and so forth. So I have now what I would call mini bands, which are well separated in energy because, I don't know if this works, but yes, it works, because I have here this large quantization condition, while here, again, this is quantized, but px is nearly, let's say kx is nearly continuous. Now, let's imagine that for some reason I have fermions, and that my Fermi level is here. Oops, what happened? That my Fermi level is here. So all these states are filled, and all the other states are empty. Now you see what happens. If I want to create an excitation, I have various possibilities. I can create an excitation inside the lower band. For example, take one particle here and change it and put it here. Or I could create excitations where I take a particle here and I send it on the upper band. And technically, if I have, for example, an interaction, everything is possible. I can do whatever. But this will cost a lot of energy. So it's essentially forbidden. So as long as my interaction, the energy I have at my disposal is of the order of what? The energy I have at my disposal is of the order of U, or the temperature, or whatever external probe I have on the problem, frequency, or blah, blah, blah. So as long as this difference of energies, this typical energy here, the temperature, the frequency, are smaller than this interval of energy here, I cannot excite quantum numbers on px. I cannot change px. So if all this delta E are, I don't know how to call it here, let's call it whatever. Let's say here, let's call it E0. If delta E is much smaller than E0, I cannot change px. Which means I have a quantum problem in which only the quantum number pz can change. And if I have a problem for which only the quantum number pz can change, it means it's a one-dimensional problem. It doesn't mean that the wave function is one-dimensional. It means that the transverse degrees of freedom of the wave function are completely frozen. So my wave function has a certain shape here, but it can never change. And the only thing that can change are the plane wave-like degree of freedom along the tube. So 1D problems would never exist without quantum mechanics. They can only exist, or of course you would need to do a really zero-dimensional object, or to have billiard balls that really cannot cross on a classical object. But if you imagine atoms, there is no way you're going to confine atoms with a precision which corresponds to, quote, the size of the atoms. But their wave function in a confinement potential can be sufficiently blocked so that you cannot excite the additional degrees of freedom. So 1D exists because of quantum mechanics, so you just need to make confinement strong enough to fix the transverse quantum numbers.
Of course, in electromagnetism you could do.
Oh, you could even do with classical particles, but it's hard. It's very hard. I mean, the condition that I'm giving you here is much more lax than trying to make really objects that whose size, intrinsic size in vacuum, would be matched by the precision. So it's very hard to really. Let me say it that way. I think without quantum mechanics, it would be much more difficult to get 1D systems. I'm not saying impossible, but I'm saying it would be very hard.
I'm saying this because still, quantum mechanics is still wave mechanics in a sense.
Yes.
Like, so Maxwell equation could still do the...
Same condition. Same condition. Of course, what I'm telling applies to any wave, as usual, so same condition. You have a wave for which you don't want to change the transverse degree of freedom. Let me give you a second possibility to realize one-dimensional systems, and this is slightly different. So let's imagine now, so second possibility, let's imagine that I have particles now moving on a lattice, because both this possibility exist in nature with a hopping which I will call T parallel and a hopping which I will call T perp. So let's say I have an Hamiltonian which is minus T parallel sum over, let's say, I and j nearest neighbor C dagger I Cj plus Hermitian conjugate, and then I will have minus T perp sum over ij or I prime j prime C dagger I prime Cj prime plus Hermitian conjugate. And of course it means that in K space I get something which is minus sum over K of epsilon K C dagger K Ck, and then I get an energy epsilon K which is minus 2T parallel cosine K parallel minus 2T perp cosine K perp. And that's the normal energy. Now let's assume that T perp is much smaller than T parallel. Then I will plot in the Brillouin zone, in the zone, the lines of EQ energy. So if I plot here, this is K parallel, this is K perp. And let me plot, for example, the Fermi energy, the line at a given energy. Well, I fix K parallel. So if T perp was inexistent, I would get essentially a straight line here and a straight line here. That's the surface of energy, let's say EF. Now, if I have T perp, what will happen is that I have to add a cosine to this. So I will deform this surface like this. Sorry for my poor graphic skills, but you get the idea. I will have a surface which is the surface of iso energy, of constant energy here, which is a function now of K parallel. This is, of course, going from pi, minus pi here, and pi, sorry, minus pi here, and pi here. Now, this is a 2D system. Now, at which condition can I say it would be a 1D system? Of course, if I switch off T perp, it's a 1D system. Actually, if I switch off T perp, it's many 1D systems which are uncoupled. So I get systems which are lines in which the particle can move, and these lines don't talk to each other. Okay? Well, I can do this if for some reason I blur the surface here. If I blur the surface, I'm not able to make the difference between a straight line and the blurred and the warp line. And I can blur it by two methods. One, I'm probing the system at a temperature T, which is much larger than T perp. Or I'm probing it with an energy probe, which has an energy which is much larger than T perp. In that case, what will happen is that I will blur here the line. Let's say thermal excitation, blur the line. And in that case, I'm not really able to make the difference between a 1D problem and a 3D problem. In other words, I can say it by other words, I cannot have a coherent, let's take the temperature, I cannot have coherent coupling between these tubes if by the time I'm able to hop, which is T perp minus 1, I've already encountered many thermal excitations. And so, in a way, I effectively decouple the tubes here, or the lines here, because of thermal excitations. With thermal excitation, I'm cheating you, because temperature is not really acting as a cutoff in time. With frequency or energy, I'm not cheating you. It can be proven cleanly. So here, I could put a question mark. In a way, here, I can put a check mark that I'm sure that if I probe a system at frequencies larger than the hopping time from one chain to the other, it's 1D. With temperature, it's commonly accepted it's 1D, but that's something we can discuss. Okay, so that's part of the problems we will come back. It just tells you that these are systems which will undergo what people call a dimensional crossover. Because you see that as a function of omega or T, they will be 1D at large temperature. Then they cross a certain temperature, which I will call T perp star, and then they become 2D or 3D at low temperatures. Why is it important? Because most solids will fall into this category. So the solutions that you get, or the experimental realization that you get in condensed matter, of course the crystal is 3D. So if you have chains, there will be many chains like this in the crystal. And the question is, can they talk to each other? And the answer is this depends on the temperature, or this depends on the energy. Okay? So these are two realizations that you can do about 1D systems. These are realization of what I would call isolated 1D system. You confine a system into a confinement tube or a confinement box such that the transverse dimensions are narrow enough for the quantization to kill all possibility to change the transverse quantum numbers. Or on the contrary, you're in a bulk crystals where things are coupled, but they can be so weakly coupled that temperature or frequency is effectively killing the coupling between the things. Okay, I have 2 minutes left, so we'll finish this part before we go to the solution by just fixing the notations for some models. So let me just give you models, because I'm sure you've seen them. So I will take, for example, just a couple of models with which I will work, and then we'll introduce some others. So if I am in a continuum, I could have free particles, so the model would be 1 over 2m sum over dx grad psi dagger grad psi over 2m. So this is the kinetic energy of the particles. And then I will put an interaction. So I could put an interaction which is sum over dx prime of something which is ux minus x prime rho x rho x prime. Of course, I should also put a chemical potential, which is rho of x, and I will put a 1/2 here. If you take, for example, bosons, and if you take the interaction u of x minus x prime, which is u0 delta x minus x prime, this is called the Lieb and Lininger model. And this is a very famous model which has a solution better on that. If I want to be on the lattice, I could have the same version of this model by saying that I have particles which are hopping with an amplitude which I will call t, and they are feeling, let's say, repulsion u if they are on the same side. So then my Hamiltonian would be minus t, sum over ij nearest neighbor, b dagger I, bj plus Hermitian conjugate. And then I would have u 0 over 2, and I would write sum over j of rho j minus 1. And again, I can put minus mu sum over j of rho j. This is called the Bose-Hubbard model. And this is also a very famous model. Now, if I take, so this is for bosons. If I take spins, the models which we will discuss the most often are variations. So I will, for example, take spin 1/2. So there is a model which is called the XXZ model, and we'll see variance. So this is H equal J XY against sum over ij nearest neighbor Sxi Sxj plus Syi Syj. And then one puts a different coupling along Jz. For Jz, sum over ij Szy Szj. And you can put a magnetic field minus Hz sum over j of Szj, where the S are 1/2 of the Pauli matrix. So these are the canonical spin 1/2 systems. And finally, if there are fermions, I will just give models on a lattice. So I can take, of course, exactly the same model than for bosons, both in the continuum and on the lattice. So this I will not repeat. But usually we like fermions to have spin 1/2. So I would say fermions with spin 1/2. And we'll see the relation between these models. And so let me write the most famous model, which is called the Hubbard model. And this is H equal minus T sum over ij nearest neighbor, C dagger I sigma, Cj sigma plus Hermitian conjugate. So these are fermions hopping on the lattice. The spin is conserved, so I have to sum over sigma. And then I put a repulsion, and because of the Pauli principle, I can only get particle of different spins on the same side, so I can only write this. And then again, I can put a chemical potential. I could also put a magnetic field, but I would not do it. Okay, so these are the various models that we would like to solve. And of course, as you can see, this is a very nasty proposal because we have here something which is quadratic, so all nice and good. We know how to solve this by second quantization. But then we have this part, which is psi dagger psi, and this contains a quartic part, and we have to do with this. We have to deal with this. So we'll do the break, and then after the break, we'll start to see one method. It's of course not the only method, but one method by which one can solve this problem, which is the bosonization method. Oui?
Could you please switch to a blackboard if possible, because in this way, the field of view is quite limited.
Yeah.
And,
you prefer the board?
yes, please. I mean, that's fine.
So,
yes, so like, because for example, we become really, lost.
like this. Okay. If you prefer the board, I go to the board. For me, it's the same. But I find a little bit a pity that you cannot get the transcript after that. Up to you. Take a vote and tell me for the beginning of the... Take a vote during the break with coffee and tell me after. For me, it's totally indifferent, so do whatever you prefer. Just choose whatever you prefer. Come to me with one voice at the end to tell me what you prefer. Okay, so let's continue. Let me first start by answering the questions that the various people asked me during the break. Don't hesitate to do this, and that's also maybe one interest of this thing. I will try to write more on the lowest part of the screen, so you can perhaps see longer. But in any case, you will get the transcript, so don't panic if you cannot write everything. But the interest is we can come back. So let me do the questions in order. So the first question was, can I elaborate a little bit more on this notion of the blurring here of the Fermi surface. So again, you have a material where you let's say you have a lattice. I can show you, and I will show you experimental examples. These materials exist. And let's assume that one is in a situation where T perp is much smaller than T parallel. Just to give you an order of magnitude, because I think, again, we live in a world where there is part of theory, but there is part of practicalities. In most solids, as I said, kinetic energy is of the order of 1 electron volt, 10,000 Kelvin. Let's say 1 electron volt is about 12,000 Kelvin, which means these T here are several thousand Kelvin in most materials. So it's extremely difficult to get temperatures larger than T in most normal materials, because you would need temperature of 6,000 Kelvin. You melt the equipment, you melt the lab, you melt the experimentalist, you melt everybody. But you can either make artificial materials where these T are much smaller, or you can take frequency. For example, frequency, it's much more easy to find frequencies which are electron volts. After all, the colors you see is because solids send you back light, which has been affected by the content of the solid, and these are the typical energies that correspond to optical transition in a solid. So sending light on a solid is easily putting you in this ballpark. But let's forget that for the moment. So let's assume that one has a material for which T parallel is much larger than T perp. Then let's imagine you are at super high temperature. At super high temperature, and let me do it with a temperature, although, as I said, I'm cheating you with a temperature. I would not cheat you with a frequency, because I think it's maybe more easy to visualize. I have a particle which is here. It tries to hop here. If the temperature or frequency was much larger than T parallel, it cannot do it in a coherent way before being probed or being destroyed, if you want, or affected by the temperature. So in a way, you're looking at zero-dimensional systems. There is no possibility to build a wave function which is coherent by taking all these sites. Now, I lower the temperature, I lower the frequency, and it goes below T parallel, but it's still much higher than T perp. Then I can make a wave function which is coherent along the chains here, but if I try to hop to the next chain, it will take forever. It will take a long, long time of the order of 1 over T perp. And therefore, again, I will either undergo thermal contact with the thermostat, or I will be scattered by the probe, which means I don't care what happens on the next chain. I don't have the time to investigate what happens on the next chain. In energy language, what does it mean? It means that if I look at the transition that I can do between a point here of the Fermi surface to another point here, each one of these transitions will have an uncertainty which is of the order of the energy that I can either exchange with the thermostat or the inverse frequency, which is the typical time by the Heisenberg uncertainty relation, delta T, delta omega is h bar, which corresponds to the time at which I'm probing my system. And so I'm not really able to make the difference on the fact that this point here is precisely here, this point is precisely there, it could be there, it could be there, it could be there. And so as a result, I cannot make really the difference between a system which would have this energy, the red energy, and a system which would have an energy which is totally flat in K-perp, which would be exactly a strict one-dimensional system. If I set T-perp equals 0, my energy is totally independent of K-perp. So again, if you think in these terms, you would see, okay, there is here, if you want, also a line which is T parallel star, which would say 0D here. But in practice, if you think in this line, you see that now you cannot make in this regime really the difference between a totally flat Fermi surface here, which would correspond to T-perp equals 0, and a Fermi surface in which there is the T-perp, which means that essentially there is this warping of the energy. So that's a visual thing. Of course, life is not as simple as I said, in the sense that this scale here is most likely not T-perp. Because the interaction, it would be T-perp for free particles. But as soon as you will put interactions, they might change the scale. So this scale might be higher, might be lower, you don't know. The only thing we know is for free particles, for which I can draw the Fermi surface. We will have to rediscuss this when we put interaction. Actually, people investigated this by RG, and this scale is actually pushed down by interactions. So interactions make the system more one-dimensional, but this is for another day. Okay. So are there still questions on this part? Is it clear, this way of realizing 1D system? So in a way, it's not at t equals 0, the system would be 2D or 3D, as it should, but it's at intermediate energy scale, it is essentially 1D. It's clear? Okay, if it's clear, let me go with the models. I went very fast, but I wanted to give you the list of models. Now, here, density. Of course, the density is connected to the field by the usual relation. It's psi dagger x, psi x. It's measuring the number of particles in one point. On the lattice, the density is rho on side j is b dagger j, bj. The fact that it's written here with a rho minus 1, it's a pure convention. I can remove the 1. As you see, this is a term which is proportional to rho, so it just modifies what is the chemical potential. At the end of the day, I don't care about the chemical potential. What I want to fix is the number of particles on the system. So I just need to define my chemical potential the way I like. The advantage of writing the interaction in this form is that the eigenvalues of the density operator are, of course, 0, 1, 2, 3, 4, 5, 6. I can have 0, 1, 2, 3, 4, 5, 6, and so on, particle on the site. So you see that this object gives you what you expect. If I have 0 particle on the site, no interaction. If I have 1 particle on the site, no interaction. 1 times 0 is no interaction. An interaction only starts if I put 2 particles and more on the site. So it's a nice way to write it. But again, if you don't like the 1, just put the 1 in the chemical potential. That's exactly the same. Here, of course, for the spins, you can define more general models, and we'll discuss some of them. I could break the symmetry between the XX and YY direction. Then it's called the XYZ model. Haha, very, very, very subtle. The reason why people choose here to separate JZ is because, for example, when you put a magnetic field along Z, well, it's nice to treat SZ separately. It's also because it has nice contact with other models that we will discuss. But of course, all the generalization of this model are possible. That's clear. For the fermions, could I define a model which would be like this one for fermions? Would it be an interesting model? It would be free. because if my fermions don't have spins, then I cannot put two fermions on the same site, so my interaction will be always 0. So for spinless fermions, what people do, they usually put a nearest neighbor interaction. So because, of course, on site, there is no possibility of interaction. But you can define a model very similar to this one, which is called the TV model, because they didn't want to call it U, they called it V. So this is also a model that you can, so this is the so-called TV model, where you write minus T sum over ij, C dagger I, Cj plus Emission conjugate, and then you put V sum over J of rho J plus 1, and then again minus mu sum over J rho J. For Hubbard model, so fermions with spin 1/2, of course here sigma denotes the two eigenstates of spin. You can take any quantization axis you like, as Z, for example. So this is either up and down. Okay. Now, you could complain that I wrote a very strange U. Okay? Not like the other one. So I let you do as an exercise. And we can correct tomorrow. I never know if in English there is a C or a exercise. Problem. So what would be the model with U over 2 sum over J rho J minus 1? But of course, because now I have two spin species, rho J is rho J up plus rho J down. And again, rho J sigma is C dagger J sigma, Cj sigma, as usual. Would I get a different model? Would I get the same model? I let you do it as an exercise. You can take your bets. Okay, are there other questions on this part? No? Good? Then we start with the beef. So, we know what is a 1D system. We have our models. And then 3. So let's do even a second chapter. And let's see this technique. So let me give you first the basic problem and ID. So let's take, just for sake of simplicity, I will take the Lieb-Lininger model. And I will try to write lower. That way you can see better. So let me remind you what is the model that I'm talking about. So I have bosons in a continuum. So I have my free particles, which are moving in a continuum. And I have my interaction, dx prime. I can put 1/2 here. U of x minus x prime, rho of x prime. I can even, if since it's an interaction, I could even subtract the average density. Again, these are modifications of the chemical potential, rho of x prime minus rho 0. And again, I could put minus mu sum over dx of rho of x minus rho 0, where rho 0 would be the average density of the particles. And I need to solve it. So the first attempt that you can do, okay, there you can see, is to say, let me use standard diagrammatic theory. So standard diagrammatic theory would mean that I'm rewriting this model in k-space. So I would write H is equal to sum over k of epsilon k, b dagger k, bk, where epsilon k is k square over 2m. And of course, I assume that you're familiar with all this technology, so if you're not, shout. No shout? Yep. There are two masses. This mass here, oh yeah, too many masses, you're right. It's the linear model for the masses. That's the, yeah, sorry. Okay, so, okay. And then I would need to write this term here in standard many-body theory. So if I was doing this, I would write a term here which is plus sum over k, k prime, and q of u of q, b dagger k plus q, b dagger k prime minus q, bk prime, bk, which would be the diagram corresponding to saying I have a boson which arrived with momentum k, one with momentum k prime. They are scattered, in a state k plus u. They are scattered in a state k prime minus q. And the matrix element is u of q. That's all very nice, but then you see that I have here something which is quadratic. So quadratic, no problem. We know how to deal with quadratic forms. But then I have here something which is for boson term, and then I don't know what to do. So you could try perturbation theory. So if you do perturbation, then you find that your perturbation is divergent. And I won't show it to you, but you get logs all over the place. You get things which explode in your face. And the physical reason why the perturbation is divergent, what does it mean doing perturbation? It means that at the end, the answer is not very different from the free term. The divergence in perturbation theory is the way for the perturbation theory to tell you the final answer is very different from your starting point. It's only when the final answer is very close to the starting point that perturbation theory is nice. Okay? Log of 1 plus x is x, which is not very different from 0 around 0. Okay? But here it tells you that essentially it blows up in your face. And this corresponds to what you saw in the slide. The initial starting point is done in terms of individual bosonic excitations. And we discussed that as soon as you put interactions, everything will be transformed into collective excitations. So there is no way your perturbation theory in U can be small, because at the end you will have something which doesn't look at all like free bosons. By the way, what is the solution for free bosons? What is the ground state for free bosons? What happens? They are all in k equals 0. These are bosons, so they just go stupidly where the energy is the lowest. So you get all the bosons. So free bosons, they are all in k equals 0 state. So the wave function is essentially b dagger 0 to the power n, suitably normalized. And the excitations have energy epsilon k equal k squared over 2. So perturbation is divergent. Now I could try to do mean field. So I could say psi of x is psi 0 exponential of I theta, where theta and psi 0 are numbers. This is what you do in 3D if you want to solve. You say, I have a superfluid, and the phase of the wave function is fixed. And then you start doing perturbation on the top of the superfluid. I won't do this. It's hopeless. Again, it will diverge. And the reason, we'll see later, is because in 1D, you're not allowed to break a continuous symmetry. It's forbidden because of quantum fluctuation, so the phase symmetry of the wave function cannot be broken. Just the same way, then the XY model in dimension 2 and below cannot have a finite magnetization. You cannot have a finite ordered phase in 1D for a wave function. 1D quantum is 1 plus 1, if you want, so it's the same idea. So we have to do something else. Okay, so the something else took a long time in the making. So either you solve the model exactly. This is what Lieb and Lininger did, and this is remarkable. You can analyze this model, or you have to find another solution. So I will give you the sort of field theory. We will discuss other limits and other possibility. I give you as an exercise until tomorrow to solve this model in the limit where the repulsion between bosons is infinite. So let's imagine that I have a finite repulsion for the moment. So I can still pile up 5 bosons on the same point in space. But let's imagine that I let you go to infinity first. So, sorry. Did I took the Lieb-Lininger model? I cheated you. So I should say here it's U0 delta of x minus x prime. I have a delta function repulsion for this model. I can take a more general interaction, but for this model, I have a delta function. So I pretend that this model has a simple solution if U0 is strictly infinite. So I let you do as an exercise. You will tell me tomorrow what is the solution of this model. What is the ground state and so on. Don't try the correlation functions. Yeah. Around U equal infinity? No, it's not obvious, but it will also fail. For reasons that will become clear once we have worked out the field theory. So yes, you could imagine something like this. You say, haha, I have the exactly solvable point at U equal infinity. Now I will expand around this point in whatever, 1 over U or something like this. It's also for the same reasons. But it's a very good question. So let's go back to this. Ask me the question again tomorrow. Okay, so let's start the bosonization. So the idea of the solution is to say, and again, it's not the only solution. As I said, this model has an exact solution by Bethe-Ansatz. There are many ways to skin a Schrödinger's cat, but this is the one we will use. So the idea is very simple. Let's try to use the physical input that we have, which we know that everything will be transformed into collective excitation. So the idea is that using the basis of individual excitation for the bosons is not a good basis. So let's try if we can use another basis. So we'll do a change of basis, except it's a very complicated change of basis in terms of collective excitations. And as you learned in the previous course, collective excitations means density fluctuations or current fluctuations. So let's try to see if we can express this problem in terms of collective excitations. And so there are various ways to do this. I will give you the version which I like, which is due to FDM Haldane. And this is PRL 471840. And this was done in 81. So this technique, the bosonization technique, is much more ancient than this paper, and it existed a long time ago. But this was initially invented for fermions. And it was re-expressing fermionic problems in terms of collective excitations, which are density fluctuations and currents, which are, of course, bosonic type excitations. Hence the name, bosonization. But I will show you that you can bosonize bosons. It has nothing to do with the change of statistics. I think it should be called collectivization, but this is a name that carries a little bit of history, so we'll stick with bosonization. Okay? So, for that, let's re-express the density operator. So let's consider a problem in which I would say there is no lattice. I'm in the continuum, but let's say I have particles which are at certain positions, and I purposefully put them relatively regular, but I don't care at that stage. So the density operator, rho of x, is the sum over all the particle of delta of x minus xi, where xi is the position of the particle. X is an operator, it's not a number. So if you want, put a hat, if you want, on the operator. So this is the density. And you see that the density is a catastrophe, because if I plot the density with a given position of the particle, this is something that is extremely discontinuous. It's 0 and bam, infinity, 0, infinity. So I have no simple way to do an hydrodynamic limit of this operator. Even if I say I want only to look at things relatively smoothed out, yes, if I look at the distance which is much larger than the distance between the particles, then I can say I have an average density and it varies a little bit. But if I want to look at the precise point in my sample, here I get infinity, here I get 0. So this operator has no smooth limit. So the idea will be to rewrite it in a form which is a little bit more pleasant, and that we can, for which we can sort of give an hydrodynamic limit. So for that, let me introduce a field. So I will introduce something which I will call phi L of x, such that I get a particle when phi L of x is equal to 2 pi times an integer. Okay? So it sounds a little bit crazy as an idea, but actually it's not totally stupid. So let's try to plot, for example, phi L of x. So what would happen if I have a phi L of x, which is a straight line? Well, that's easy. When this is equal to 2 pi, I get a particle here. When it's equal to 4 pi, I get a particle here, and so on, and so forth. So, for example, for the phi L of x that I draw here, what do I get? I get a crystal of bosons. I get particles which are completely spaced regularly. So if I take phi L of x, which would be rho 0 times x, I get particles separated by rho 0 minus 1. So this is a crystal. But now I could, for example, take another form for phi L of x. So you see that if I take something which instead of being straight would be something like this, then I would get here my first particle, here I would get my second particle closer, my third particle would be a little bit further, my fourth particle would be somewhere here, my fifth would be somewhere there, and so on and so forth. So I can describe any configuration by just distorting this field phi L a little bit compared to the diagonal. And unless I get some crazy configuration, so I'm not allowed to do something like this. 1, 2, 3 bosons here. Then phi L would have very strong discontinuity. I would have 2 pi, 4 pi, 6 pi. If I want to pile up many bosons on the same site. But if I say interaction will discourage these configurations, most likely what I will get are distortion of phi L which would be not too strong compared to my diagonal. Sorry? Sorry. Yes, there are many phi's which corresponds to the same position of the particles. And again, we will try to choose the most reasonable one compared to the diagonal. So the smoothest one. The idea will be to do an hydrodynamic description in terms of phi L. So we want the field as smooth as we can. Okay? So yeah, but that's exactly the point. I don't want to, certainly if I have a strong repulsion, I will not want to pile 5 particles on the same point. So these configurations are certainly extremely unlikely or cost a lot of energy. For small repulsion, we can discuss. So let me advance with my phi L, and then we can discuss the limit of validity of this. Okay, so if I buy the principle of this, I can rewrite my density, which is sum of delta x minus xi. I can rewrite it as a sum over n of delta of phi L of x minus 2 pi n. But I have a Jacobian, and I won't get rid of the Jacobian, and the Jacobian is the modulus of gradient of phi L. So this is an identity. If you take the standard formula on delta function, and you say every time I get a particle, it means that phi L is equal to 2 pi n, you can rewrite this thing in the most complicated form, which is this one, and you have to use this as the Jacobian of the transformation. Okay. Now you would say it's very nice, but what is the use? Well, the use is that I get a Dirac-Combe here. So I can rewrite my Dirac-Combe in another way, which is that I can rewrite my density, rho of x, as the modulus of grad x of phi L. Oops. Grad x of phi L of x times the sum of a p, modulo normalization, which is not important, exponential of I p times phi L, phi L of x. So this is just an identity for representing Dirac-Combe. You see that essentially here, if phi L is equal to 2 pi n, then this phase here is 2 pi times an integer times another integer. So all the waves here are adding up, giving you infinity. If phi L is not equal to 2 pi times an integer, by doing this summation here, I get interference. The sum gives 0. So this is standard representation of Dirac-Combe. If you want, we can go more in details in the calculation, but this is an identity, essentially. That's the Fourier transform, if you want, of the Dirac-Combe. Okay, so now you see that I have an extremely complicated representation of the density operator in terms of this field phi L. Yeah.
Why will we just write then rho of x as a Fourier series? So like, and then a smooth function, and then we don't need to reduce.
No, it won't, because you still need the fact that the density is essentially a delta function. So you need all the terms of the Fourier series if you want to do it that way. But perhaps you can wait, let's say, 10 minutes and ask me the question again. Okay? Okay. So now let me assume that phi L is not too different from the diagonal. So I will assume that phi L of x is equal to 2 pi rho 0 times x. And sorry, I said here, I forgot a 2 pi here. And this is, if I want particles separated by rho 0 minus 1, and I want the product rho 0 times x to be an integer, and the 2 pi has to be here in the definition. Okay, so let me take phi L of x is 2 pi rho 0 x minus a field which I will call here 2 phi of x. So if you want, it's the definition of the field phi of x. It's the deviation compared to the diagonal. I can rewrite my density, rho of x, as what? As oh, sorry, there is a normalization here which I should have put, which is 1 over 2 pi. Again, that's fixed. So the first term is essentially 2 pi rho 0 divided by 2 pi. So this is rho 0 minus 1 over 2 pi gradient blah, blah, blah. So this makes 1 over pi gradient of phi of x. And then I get the sum over p of exponential of I 2p times pi rho 0 x minus phi of x. And now you could say I've become nuts because essentially what I did was to rewrite in an extremely complicated way the operator density, which was written much more simply in terms of the x. I've written this operator much more complicated, in a much more complicated way in terms of this field phi. Okay, but now let's try to examine a little bit what does it mean physically. I'm sorry, just when should I stop? 1:10, perfect. Good timing. Okay, so let's first consider in this sum the term p equals 0. If I consider in this sum the term p equals 0, and let me first consider that I have phi equals 0. If I have phi equals 0, my density corresponds to regularly spaced particles, as we were discussing before. Okay? Now, this term will correct the density, and let's assume phi is a smooth field, so that phi of x varies slowly. If I assume that phi of x varies slowly at the scale of rho 0 minus 1, which is the average distance between particles. Well, you see that this first term will correct the density. So, for example, if the gradient of phi of x is negative, I will increase the density. If the gradient of phi of x is positive, I will decrease the density. So what would happen if I have a phi of x, which is, for example, something like this? Well, it means that here my particle, the gradient will be, the gradient will be negative, so I will increase the density. So it means that instead of being at the position the particle should be, it will go a little bit here on the right. Here, it will be a little bit on the left, so that the density here has increased. So rho, this is rho of x. So this term is just the hydrodynamic term of the density. Think of phi as the displacement of the particle compared to their perfect equilibrium position. So if you think in terms of elasticity, phi is the displacement of the particles. That's perfect. That's the hydrodynamic term. That's the one you heard in the previous talk, in the sense that's the small deviations. So you see that phi has a very simple interpretation. That's the hydrodynamic term telling you what is the variation of density, but at a scale which is much larger than the lattice spacing. Now let's look at the other terms. Let's look now at the term p equal 1. And let me keep things simple. I will consider that phi is constant over a large portion of the system. And I will consider what happens if I say phi is a constant. If phi is a constant, then the density is essentially rho 0 cosine 2 pi rho 0 x minus 2 phi. Now, what does it mean? It means that my density is a perfect density wave. So here it's high, here it's high, here it's high, here it's high, and so on, except because this is a cosine, so this is a density wave with exactly the periodicity corresponding to the average distance between the particles. And now phi shifts these waves right and left. So depending on what is the value of phi, this wave will be displaced. It will be here. But it doesn't change the average periodicity. Sorry for the drawing. This is shifted by 2 phi. 2 phi divided by blah blah by 2 pi. Okay? So you see that what you do when you write this formula, you write actually a Fourier decomposition of the density. Because now if I pile up more waves, p equal 2, p equal 3, p equal 4, I will do interference which will reproduce the delta function at the place where the maxima are. So I found a way, or rather Haldane found a way, to write a Fourier decomposition of the density that keeps the fact that the operator is not smooth. If you sum over all this p, the operator will not be smooth. It will have delta function at the actual position of the particles. But now it's not expressed in terms of a field which we don't control. It's expressed in terms of a field here, which is a smooth field at the scale corresponding to the lattice spacing of the particle. So for this field phi, I can try to write an effective action of the type that Jerome wrote before, which will be an hydrodynamic action. And the point is that I can encode the complexity of the operators not in the field phi, which will be a smooth field, but in the form of the operator itself. So the bosonization consists in two things. It consists in writing the right finding the right hydrodynamic variables. We're still missing one. I'll tell you what it is. But we need this second variable. But more importantly, it's to write the operators in terms of these hydrodynamic variables. But it's very important to remember that the operators are not hydrodynamics. They are not averaged at the distance which is corresponding to the lattice spacing. Actually, you can make predictions at distances which are much smaller than the lattice spacing. The price to pay is that the operators become complicated. So you encode the complication of the operator in the form of the operator, but they are expressed in terms of a smooth field. And that's the idea of the method. Yes?
So what is like the collectiveness? Or like so what is the collective excitation? Where is the underlying the collective excitation?
So here, for example, phi is the variable, the field, that will control a collective excitation, which is to produce waves in the density of the system. So if phi is a constant, of course, no excitation is produced. You get a perfect crystal. But when phi will fluctuate, the density of the system, not an individual particle, but the whole density of the system will fluctuate. For example, if phi was linear in time, constant in space but linear in time, the whole wave would slide. Because now you're shifting the phase by something which would grow in time. If I increase phi locally, particle will collect at one point, and so on. So this is one of the collective variables. As I said, we need a second one. And since I have 1 minute, I will give you the second variable, and we will exploit it tomorrow. So what is the second variable? Well, I gave you the density. The density is essentially the square of the wave function. So the second variable has to come from the wave function itself. So I will write the single particle wave function, psi of x, as the square root of the density, square root of rho of x, which is fine, but then I need a phase. So let me multiply this by a phase, and let's try not to cheat you on the sign, although at that stage it's totally unimportant, but it's exponential of I theta of x. So this phase is an operator here. And now you see that I have this object, which is the collective excitations of density, which is controlled by the phase phi, which again is an operator, but which can be smooth, for which I can have an hydrodynamic representation. And I have a second phase here, which tells me what is the phase of the wave function. And of course, if I add a superfluid, the phase will be constant in space and time. Now, this phase can fluctuate. And of course, I will need both phi of x and theta of x are my smooth collective excitations. Let's say variables. So I need to do two things, which we will do tomorrow, which is find a relation between the phase phi and the phase theta, because most likely they are not independent. And you can already guess what will be the relation. It's like with any superconductor. If I know exactly where the density is, my phase of the wave function fluctuates like crazy. If I fix the phase of the wave function, the number at one point fluctuate like crazy. So phi and theta are kind of canonically conjugate. That's the thing. And then the second thing we need to do is to write the effective action, the effective Hamiltonian, in terms of this phase phi and theta. And actually, this is where the magic will operate, because once we've done that, the Hamiltonian is quadratic. And that's it, we have solved the problem. Yeah.
Where does the rapidity come in then?
Where, sorry?
Where does the rapidity come in, sort of, in terms of the last equation that we have?
You mean the speed of sound or the velocity?
Yeah, the speed of the connection.
It will come. It will come. So that's something we will do tomorrow. So I think it's a good time to stop. And if you have questions, I take them. Otherwise, we do it either in the afternoon session if there is discussion or during lunch. Okay, let's stop here.